How many people registered for the conference, Professor Shaw?
Okay, sir, good morning. Can you start, sir?
I can hear.
Sir, can you start?
Yes, we can start.
Yes. A very good morning to all. Let's start the fresh day with an eminent speaker. It's my great pleasure to welcome you to the 2022 IEEE IAS Global Conference on Emerging Technologies. I take this opportunity to welcome our keynote speaker, Chris May. Professor Chris May is the distinguished professor and the chair of the Department of Electrical and Computer Engineering at San Diego State University. He is a fellow of IEEE, Institute of Electrical and Electronics Engineering, and Society of Automotive Engineers. He is the director of the US Department of Energy-Funded Graduate Automotive Technology Education, Center for Electric Drive Transportation at SDSU. He is previously a faculty member at the University of Michigan from 2001 to 2015 and electrical engineer with General Electric from 2000 to 2001. He also served as the CTO of One Power Solution from 2008 to 2011. Dr. Mee received his PhD from the University of Toronto, Canada in 2001. Dr. Mee has published 5 books, 204 journal papers, 126 conference papers, and 25 issued and pending patents. He served as an editor-in-chief, area editor, guest editor, and associate editor of multiple IEEE transactions and international journals, as well as general chair of over 10 IEEE conferences. Dr. Mee has won numerous awards, including the Distinguished Teaching Award and Distinguished Research Award from the University of Michigan, Dearborn, IEEE Region 4 Outstanding Engineering Award, IEEE Southern Michigan Section Outstanding Professional Award, and SAE Environmental Excellence in Transportation E2T Award. He is the recipient of 3 Best Paper Awards from IEEE Transactions on Power Electronics and the 2007 ECCE Student Demonstration Award. In 2019, he received the inaugural IEEE Power Electronics Emerging Technology Award. In 2022, he received the Albert W. Johnson Research Lectureship and named the Distinguished Professor, the highest of honor given to a SDSU faculty member, and one award is given each year. Dr. Mee was the chair and vice chair in the years 2008 to 9 and 2006 to 7, respectively, of the IEEE Southeastern Michigan section. Dr. Mee was the general chair of the 5th IEEE Vehicle Power and Propulsion Conference, area editor of IEEE Transactions on Vehicular Technology, associate editor of IEEE Transactions on Power Electronics, associate editor of IEEE Transactions on Industry Applications. He is the topic chair for the 2011 IEEE International Future Energy Challenge and general chair for the 2013 IEEE International Future Energy Challenge. Dr. Chris Mee is a distinguished lecturer of the IEEE Vehicular Technology Society. He is a guest editor in the chief of IEEE Journal of Emerging and Selected Topics in Power Electronics, a special issue on WPT, guest co-editor in chief of IEEE Transactions on Power Electronics, special issue on WPT, guest editor of IEEE Transactions on Industrial Electronics, special issues on Dynamic Wireless Transfer, and steering committee member of IEEE Transactions Electrification Conference. He is a program chair or general chair of a number of international conferences, including workshop on wireless power transfer, IEEE Electric Vehicle Conference, and IEEE Transportation International Transportation Electrification Conference, Asia Pacific. He is a guest editor of special issues for the proceeding of IEEE electric and hybrid papers. With a brief introduction, I would welcome Professor Krismi for our today's presentation. Sir, the stage is ready for you. We are ready to hear from you, sir.
Great. Thank you very much for that great introduction. It's really a pleasure and honor to speak at this wonderful conference. And I understand that this is conference is offered virtually, and the presentation is recorded. So if other people don't have a chance to listen live, they will have a chance to watch the video. Can you hear me very well? Can I go ahead?
Yes, sir.
Okay, great. Thank you. So my talk today is about the cost-effective integration of second life EV batteries with solar PV systems for commercial buildings. So basically, give you just a little bit background why we are doing this research project. First of all, grid-connected battery energy storage systems can help manage the variability of power generation from renewable energy, such as solar and wind power systems. They can help reduce peak power demand and shift the usage to suit off-peak hours so as to reduce electricity cost. However, the energy storage systems are quite expensive today. So we are turning to second life EV battery. So second life EV battery really includes those batteries that are discarded from EVs due to degraded conditions. They are no longer applicable in the EV, which means they cannot drive with the distance and speed they want, or they could be emergency replacements during road accidents, test vehicle batteries, and also unsold batteries. These batteries will be wasted, or they have to be recycled if we don't use them, but they still have energy. So we can use them for other purpose before they are recycled. So use this battery in grid BESS will extend the life cycle of batteries. Hence, they will improve the environment, reduce EV owner cost, and benefit business using these BESS systems. And then, what are the barriers? Why we can't just get the battery and use them in an energy storage system? Well, there are certain barriers that we have to overcome. So first of all, we need to develop and integrate these batteries reliably, cost-effectively, and economically. If they cost more money than buying new batteries, and then there's no point to use this battery, even though they help with environment, but they may not be interested by the businesses because they cost more money, or they don't look reliable, or they are not cost effective. So we must safely and consistently manufacture and deploy this type of energy storage systems. We need to overcome many hurdles. For example, how we can remove batteries, transport them, storage them, testing them, and select them for different applications. What is the quick, simple, and accurate estimation of this battery health conditions? How can we identify the health condition of every single cell after deployment in the grid storage? So we need to build a dynamic battery management system which can minimize the degradation of the battery and optimize the usage of this battery. So we need to overcome all these hurdles before they can become available for storage application. So in our research project, we have 5 project goals. First of all, we want to conduct aging study of second life EV batteries in the laboratory to see how they age, so that when we deploy them, we can know how exactly they will age in a storage system. And then in the laboratory, we create a second life battery genome through laboratory scale analysis to understand what is the mechanism behind the battery aging. We'll develop a battery management system associated technologies, algorithms, and operation strategies, which increase overall efficiency, total ownership cost, reduce total ownership cost, and decrease degradation. So what we are going to do is we're going to design and build 2 pilot test facilities outside the laboratory to demonstrate that the proposed technology can work reliably, efficiently, and economically. So that is our goal. In this project, we prepare the Nissan Leaf Generation 3 battery packs for site deployment. As you can see here, we have prepared 9 battery packs. Each battery pack is rated at 62 kilowatt-hour for its nominal capacity. But these batteries have been used in vehicles, so they have degraded to a certain SOH, anywhere between 80% to 95%. So you might ask, why are they 95%? Well, because some of the batteries were actually, due to warranty issues, they were removed from the vehicles early. They're not removed at end of life. Also, some other batteries were damaged during transportation. So they could not be installed on a vehicle because they have minor damage on the shell. So we use them for energy storage. We also identified demonstration site, and the site that we have found are all in San Diego, California, the United States. On the left of the screen, you can see this building has 22,000 square feet, and the system that we will develop is going to cost roughly $96,000. The lifetime savings of that building, based on our calculation, is going to be $300,000 over 10 years. It has a solar system, and we're going to build a storage system rated around 320 kilowatt-hour. On the right hand, it's another business which also houses a biotech company. This is a relatively small building, only 6,600 square feet. And the cost to install such a system is $86,000. But the savings is only $200. So over 10 years, the savings is roughly only $24,000, which is far less than the cost to install such a system. So then the question is that why? Well, because the owner of this building have told us that they needed an energy storage system for resilient operation. Because if power outage happens, they can lose their buying samples. In 24 hours, they will lose $50,000. In 48 hours, they will lose more than $100,000. So this energy storage system can last 24 hours. It can help them to prevent the loss. So this is why we are building the second system, not for savings of electricity, but to prevent losses due to power outage. So let me move on to the laboratory study. How do we characterize the second life battery and develop the aging model? So in the battery space, you have so many. Apparently, we cannot test all kinds of battery. So we selected 4 typical batteries for laboratory study. The first case is a Nissan Leaf Generation 1 battery. It is a 24 kilowatt-hour lithium manganese oxide that was installed in Nissan vehicles between 2012 to 2020. Some of the batteries have been running for 8 to 10 years. We tested over 100 packs, and we found those batteries are anywhere from 60 to 70% of its original capacity. Our case 2 is Nissan Leaf Generation 3 batteries. It is rated at 62 kilowatt-hour. It's lithium, nickel, manganese, cobalt type of battery. They were installed on these vehicles since 2018. So they were running for 2 to 4 years now. We tested 20 plus battery packs, and we found their capacity is anywhere from 89% to 97%. Our case 3 involves a battery from electrical forklift. They are 100 ampere hour batteries that have been used in this forklift for 4 years. And their cell capacity, when we tested, is around 89 SOH. However, when we test the pack, they are only rated, not rated, but they only have 50 to 60% SOH left in the pack. The reason is a balancing issue. The last type of battery we tested is from an electric bus, which is a 270-hour battery. They are retired after about 4 years. And these battery modules, at the cell level, they maintain roughly 80% of its original capacity. But at the module level, the capacity is only 52. Therefore, these batteries also have a huge balancing issue. I want to give you actually a conclusion before I go into the details how we tested. The reason is that very simple. We tested 4 batteries. We did the laboratory study. We built the aging models. How are they? Can they qualify for second life storage application? It turned out, yes. It depends. For Nissan Leaf Gen 1 battery, these batteries are very good batteries. Even though they are only 60 to 67% of its original capacity, they can still run for energy storage application for many dozen cycles, probably 10 to 15 years, as you can look at the bottom of the slide. The reason is that these lithium-ion phosphate batteries are very linear. Their degradation is very linear. They don't have an aging need. Our second battery is a Gen 3. Even though they start with 89 to 97% of its original capacity, they also have about 5% very minor balance issues, but they can run also for roughly 10 years, about 3,000 cycles. But they do reach aging need at around 75% SOH, which is about 1,500 cycles. It means that this battery doesn't last that long once they reach their aging need. Our third type is also lithium iron phosphate battery. So they can last also a very long time, even 20 years in their second life, because they have 89% SOH to start with. But at the pack level, because the series balance issue, we need to address the balancing problem within the pack if we directly use the battery pack. Similarly, the last battery type is the same. They have a very linear degradation and they can last for a long time, but we need to address the balancing issue for those battery packs. So if you look at the battery packs we tested, on the top left corner, we tested about 100 Gen 1 batteries. In the middle, that's the 2 battery packs we tested inside the laboratory with a detailed aging study. At the bottom is the aging cell, that we tested. On the top right corner, that's the battery we tested for the Gen 2 battery. At bottom right corner is the 24 battery cells we tested for the Nissan Leaf Gen 3 battery. How did we get the battery cell to test? Well, we actually disassembled a battery pack from the left, and then we get the module in the middle, and then we disassemble the module to get the battery cells at the bottom. So we get 28 battery cells, and we tested 24 of them. And we also tested a battery module. I will explain to you the results later. This one shows how we test the batteries using RB BT2000 to test those Nissan Gen 1 and also the forklift batteries. And this one shows how we test the batteries, the Nissan Leaf Gen 3 batteries. In the middle, you can see it's the room temperature. On the left hand, we test the batteries inside the thermal chamber at 35 degrees C. On the right hand, we test the battery in another thermal chamber at 10 degrees C. And the aging test result, detailed result, is showing for a few different batteries here. The first one is Gen 1, Nissan Leaf Gen 1 battery. As you can see from the top, the capacity of the battery cells, they degrade. They do degrade. They started around 42 ampere hours, and they degrade all the way to roughly 30 when they reach roughly 4,500 cycles. So this is very linear. So this lasts a long time. The bottom graph shows the internal impedance. As you can see, the internal impedance does increase over time. As you can see, around 3,000 cycle, before 3,000 cycle, again, this is only second life cycle, does not include their first life in the vehicles. So before 3,000 second life cycle, they are quite stable. Therefore, the 3,000 cycle is guaranteed in second life years. Beyond 3,000 cycles, as you can see, the impedance start to increase quite dramatically. Now, even though the degradation from the top is still linear, but the impedance does increase quite quickly. So they are still good for use in storage application. The only attention we have to pay is that we cannot discharge or charge them at a high C rate, because that's going to increase the loss inside, and they're going to help or speed up the degradation. So therefore, if we want to continue to use them after 3,000 cycles, roughly before 6,000 cycles, we can still charge them at a much lower rate, so they can still be used in energy storage application. The Gen 3 battery test result is quite dramatic. As you can see from the top graph, some of the batteries in the second life should aging need around 1,000 cycles. Other batteries showing aging need around 1,900 to 2,000 cycles. The reason is that for the aging need that happened earlier, we charge them at a higher rate. For the aging need that happened at a later time, their charge and discharge rate was smaller. If we continue to decrease the charge and discharge rate, as you can see from some of the curves here, they tend to go back to maintain their capacity for a little bit longer time. And also from the bottom, you can see the impedance increased dramatically at the point they reach the aging need. And it's not a simple like a percentage increase, it's many times increase. So therefore, our conclusion that once this battery reaching the aging need, they have to be retired. We cannot continue to use them because it's dangerous. And also, if you look at the battery, after they are reach aging need, if you continue charging them at a high rate, they will start to inflate. So the battery start to swell, and they are very, very dangerous if they are continued used in any application. We wanted to compare the performance at the module level and at the cell level. So just make sure that when we disassemble the battery cells, we did not make any damage to the batteries. So we tested the battery module. As you can see from the curve on the right hand, the blue curve is the linear degradation of the pack, and the multiple curves below is the degradation of the cells. Now the blue curve is above the cell curves. The reason is that the pack started at a higher capacity, like 52.5, but the cells started roughly around 50. So therefore, they are on top. But if we shift the line a little bit, we can see that they actually overlap quite well, which means that this pack, this module and the cell degrade roughly similar pattern. And also, if you look at the bottom graph, which shows the impedance, you cannot see really the difference between the pack and the cell. So this confirms that our testing of the cell is okay. They were actually correct. The result of, let me see. After that, we did some battery genome study. So we look at the battery voltage and current performance, and we try to find where this degradation happens and why they happen. So basically, we look at the thermodynamics, we look at the kinetics, we look at the mass transport and the kinetic variation. And from there, we can identify what exactly the degradation of each cell. And we can, this is important because we need to identify this degradation, and we want to find later on, we need to look at where the knee point happens. So in reality, once the knee happens, the battery degrade very quickly and they can cause danger application. So therefore, we want to identify the knee point. Once they reach the knee point, we want to remove those batteries from the application as soon as possible. As you can see here, we look at the capacity degradation, and we come up with algorithms to identify aging knee. So basically, we look at the blue curve here. As you can see, the blue curve is basically away from the actual SOH. But once they cross the blue curve, we think this battery has reached its aging knee. So that's how we can identify. So in order to verify all these ideas, we also created coin cells in the laboratory from the large format battery cell, so that we can conduct a lot more comprehensive testing and analysis. So we did the cells and we did the testing of the coin cell. As you can see, the coin cell perform at a different current, like 0.1 milliamp, 0.2, 0.4 milliamp, and 0.6 milliamp hours. And they show certain degradation, which is consistent with the results we tested at the cell level. So this really is very robust data that we have collected. So our next task in this study is to validate this second life yield battery for solar and PV storage. How do we validate? Well, first of all, we identify these locations where we install these batteries. We install monitoring system so that we can look at the performance of the site, like how much electricity used, when they use it, how they use it, how much electricity cost they pay per month, so that later on we can do the optimization of the site. So we designed our architecture. We basically take the whole battery pack, as you can see from, let's say from the graph on the on the left hand. We have connected here 8 batteries, and each battery is connected to a DC-DC converter, and the DC output is connected to an inverter, and the inverter is connected to the grid. So we can either parallel these two output of the DC-DC, or we can also put them in series, and each one is fine. So we did this one for different applications. On the right hand, we have 4 batteries. So each battery is connected also with the inverter, with the DC-DC, and then the DC-DC output is connected with the inverter. Now, one other thing we did is to use, since we're using the battery pack, so basically we are reading the information from the battery pack. There's a BMS inside the battery pack. But one of the problems that when we put all these battery packs together, each battery pack is sending out some information which are identical to each other. So we don't know which information belongs to which battery cell inside which pack. So in order to understand the performance of each battery cell inside each battery pack, we designed a BMS gateway. So this gateway will read the information from each battery pack, and then they stamp this data and send it to our central controller. When this BMS is ready for commercialization. And we designed the thermal management system because we want to make sure that these batteries are going to operate as expected. So we don't want them to go too hot or too cold. So we designed a cooling system for the battery pack. And then we also designed the structure inside the container to hold the battery. And we designed the container to hold the battery. And we verify the strength of the container, the strength of the rack that is going to hold the battery. And we design circuit how to connect these components together. So once we design that, we'll deploy these battery packs inside in a building, near a commercial building that can supply power or store power from the building. So in order to realize optimum use of these battery packs, we have to manage all the batteries. In addition to the gateway, we have to manage the battery, the charge discharge, and we have to control the charge and discharge, not only just for the battery life, but also help the owner to save electricity. So in order to do that, we design a modular energy management system. We call it MEMS. And this MEMS collect the information of each battery pack, each battery cell, and the DC-DC converter, and the DC to AC inverter. Then they control the power distribution, like how much SOH, how much SOC, how much power from solar, how much power is used inside the building, and how we can use these batteries to realize the maximum benefits from this storage system. And one thing you might also notice that since we're using different packs, many packs inside one system, the packs may have different SOH when they come in. But we want these battery packs to last relatively the same amount of time. So therefore, we need to control the battery pack to make sure they last enough time, similar amount of time, even though they have different SOH to start with. One of the functions is to balance the battery packs during usage. So we design a balance system to control the battery packs so that they are balanced during the usage of those batteries. I mentioned earlier about the resiliency operation of the building using this energy storage system. So during a power outage, we need to detect the power outage and form an islanding operation. And this islanding operation happens when the power outage happens. And this islanding operation will take anywhere from 17 milliseconds to a couple of seconds, depends on the condition, so that we basically run almost an uninterrupted power supply for the building. So we need to disconnect the system from the utility grid, and then we start to supply power from the battery and the solar to the building. So that's how we operate the system. As you can see here, this is testing inside laboratory. It took us about 20 seconds. But in a real life application, we want them to operate, in fact, within one cycle, roughly 17 milliseconds. In order to make sure the system works and we know how it operates, we don't want somebody to sit in a container to look at how they work. So we will design, in fact, we already designed part of the system, the phone app. So this phone app can monitor in real time how each battery is performing, how the solar is generating, and how the building is using power, and whether the batteries are having any issues. So if there's any issue, it will send a notification to the app owners. And this app can be installed on many users' phones, and not just one person, but multiple users, like up to 4, 5, even maybe 10 to 20 people who can monitor the system at the same time. And lastly, as I mentioned earlier, one of the functions of this is that we want to optimize the usage of the battery, and we basically want to optimize the system such that it will help the owner to save maximum amount of money. So basically, we developed a model predictive control system. With this system, we can predict the usage of the building, and we can use that information in also including like weather forecast and any other information, historical information, to build a profile. And with this profile, we can optimize the usage. For example, if we know that the weather is bad tomorrow, then we will put more energy in the battery today so that we can use the battery energy tomorrow while we don't generate enough from the solar system. By doing this, we can reduce the demand charge of the building. Demand charge is a significant amount of charge, the cost to the building owners. So we can cut the demand charge, and also we can shift the usage to the low cost area. In California, for example, the business has to pay 65 cents during peak, but only 12 cents or even less during non-peak. So we shift the usage to the low peak, and we don't use as much power from during the peak from utility. So therefore, we can save money. As you can see here, with the original system, it was $2,922. With MPC, it can help reduce the electricity cost to $1,840, roughly $250 of savings, about 10%. But if we do better, in ideal situation, it can even do better. On this table here, you can see without MPC, the cost in this one building is $2,500, $64 per month. With method 1, we went down to $2,200, which is saving of $360. With method 2, it went down to $2,300. With method 3 and 3, it didn't change. Method 4 went to $2,200, $25. With method 5, went down to $2,187. With ideal situation, we think we can run down to $1,240. Of course, it will be very difficult to meet the ideal condition, but with all MPC, we think we can run anywhere from $1,200 to $2,100 for the owner. So that's a significant amount of savings for the building, which is the benefit of this energy storage systems. I mentioned about the battery life, because if the battery doesn't last very long, it's not going to do much good for the owner, because they might prefer to go with a new battery. So we have to control the lifespan of the battery. Because the solar generation changes and the usage changes inside the building, so we have to make sure all battery usage in a pattern that it helps increase the life. So for example, if you look at the current technology, they basically does not consider too much about the battery life. They simply might just consider the solar generation and the electrical cost. In all proposed technology will operate based on not only just grid requirement, but also we manage the charge and discharge of individual battery packs so that we can extend the battery lifetime. The other thing that when you come to a building, one of the key questions is that how much battery do I need? Like how many kilowatt hour do I need to install? If I install more battery, apparently it's going to help us save more money, but it's more cost. So my cost may not be recovered from the electricity savings. But if I don't install enough, I don't get out all the benefits, right? So there is optimal size that we have to do. So in this project, we also study the sizing of this battery energy storage system for buildings. We basically take the input such as building usage, electrical price, and demand charge, and other information, and also future expansion, and we size the battery such that the owner will get the maximum benefit, like the maximum savings, but also do not invest over as it is needed. So therefore, this is maximum return on investment. So we already finished pretty much the lab testing, the lab study, the genome study, the site design, and the optimization, the control algorithm, the gateway, and the memos. They're all done. So we are right now in the phase of doing our site construction. So with our site construction, as you can see here, this is the building. It has also a lot of solar power already, but they still don't provide enough power for the building. They still have to use like $10,000 from the utility. So therefore, they are installing in the red square another coupled solar power. At the same time, we're going to install a battery energy storage system using Second Life UV batteries for this building. And this is the side one that I introduced earlier. It's going to save the owner roughly $3,000 per month. And this is the parking lot at the back of the building. So they're going to install 120 SunPower solar panels. And at the top right corner is where the dumpster is. Next to the dumpster, we're going to install a container. And within this container, we're going to install 6 battery packs. Those batteries are rated at 62 kilowatt hour each. And they will be mounted on the concrete. And we're going to run a conduit from the container to the building at the bottom where the electrical room is. We purposely make this container a little bit from the building. So in case there's a safety issue, this container will not impact the building, like it's not going to burn down the building. And this is showing where the building is located, where the electrical room of the building, and so on. And therefore, the container that we design is going to include 6 Nissan Leaf Gen 2 battery packs, 62 kilowatt hour each. That's the nominal value. The actual capacity is anywhere from 50 to like 56 kilowatt hour. And we're going to connect this 6 batteries with 3 DC-DC converters, and the output of the DC-DC is connected with inverter, and they're going to be connected to 208 400 amp circuit disk, and also connect to a PV system. And this is our one-line diagram for the building before, and this one-line diagram after the building install new solar and a new battery system. The battery system and new solar is shown on the left hand of the diagram. As you can see, the inverters, DC-DCs, and the disconnectors, the utility meters. We're going to monitor the whole performance of the building. And that's what we're going to do for our second UV life battery. Now, at the end of this talk, I just want to introduce you some of the other research that is going on in our laboratory. I consider this as my second project. It's the battery safety and management system study. As you know, that a lot of battery fires, whether it's Tesla, whether it's physical karma or any other battery, many of the accidents, even in a Boeing 787. So we are going to have to deal with battery fire once in a while. So how to make these batteries safe and like identify those potential issues ahead of catastrophic events is very important. So we focus a lot on this study. Another project in our laboratory is wireless charging, and our group have developed a number of topologies that are kind of very highly cited, including the double-sided LCC topology, which is recommended by the SAE G2954 for electric vehicle charging. And another one is LC's capacitive wireless charging, which is the pioneer work in the wireless charging area. So this apparently is very important. We also have done some work in foreign object detection in wireless charging systems. So hopefully all this technology that we develop and all scholars, researchers around the world, is going to pave the way for the commercialization of wireless charging in the next couple of years. Another project is very interesting one we're doing right now is aviation. As you know that aviation consumes like 2% of CO2 emissions and 3% of all greenhouse gas emissions. And electrical airplanes is still unreal because the batteries are too heavy to be put on electrical airplanes. But long haul, not possible. But eVTOL, what is eVTOL? eVTOL is electrical, vertical takeoff, and vertical landing electrical vehicle. And these vehicles are not very big. They don't travel very far, but they can be used, for example, for emergency operations, for food delivery during disaster, and for medical operations. And you might ask, why? Can we just use helicopters? Yes, you can. But helicopters are very slow and very noisy. It really is not optimal solution. Now, can we use just jets? Well, jets, yes, they do travel very fast. They can even travel a long time, carry a lot of people and goods, but they need a runway. So how can you transport somebody from hospital A to hospital B in another city, for example, during a transplant? It's very difficult. With this eVTOLs, we can do that very quickly because they can take off vertically within seconds, and they can cruise at a much higher speed than a helicopter, typically at about 300 to 400 miles per hour, and they can land vertically on even the top of a hospital building. So this is a very, very new technology, and it's very important. So we are doing this with NASA and to design this airplane, and my work is primarily in the propulsion system design. And over the past 20 plus years, we have done a lot of work in batteries, electric vehicles, and we are wireless charging, battery management, and so on. So along the way, we have also written quite a few textbooks. and they are also listed here. So if you have an interest, you're welcome to browse them. And they are also available in different languages as well, including Chinese, German, and I believe Korean as well. So if you have an interest, please feel free to search on the internet or on Evernote. With that, I want to thank my students, my postdocs. They work really hard on all these projects, and I also want to thank California Energy Commission for this particular research project and other projects and all other funding agencies that help my research in the past 20+ years. I think this is the end of my presentation, and I'll be happy to answer any questions you might have.
Thank you so much, sir. And we have a few questions from the author side too.
Okay.
Yes, there is a question from Dr. Teng asking question like, when you do the experimental works to validate energy efficiency model, you can tell me the environmental testing including the environmental temperature, pressure, humidity, etc. Will you check that?
Is it in the chat?
It's in the question answer section, sir.
Question and answer. Okay. Okay. Yes, I see that. Okay. So it says, I have some questions. When you do the equipment experiment works to validate the energy efficiency model, you can tell me the environmental testing, environment including the environment temperature, pressure. Yeah. Why do you use model predictive control to energy system? Yes. Good question. Very good question. Well, in the environmental testing, we only focus on the temperature. We don't test the humidity or any other or pressure, anything. So the temperature we run at 3 temperatures. One is 10 degrees C. The other one is at the room, 25 degrees C. And last one is 35 degrees C. We know these lithium-ion batteries don't work very well at low temperature. They also tend to be dangerous if they work at a high temperature. So if we want to look at the performance at these temperatures, basically we have found that the higher temperature have more degradation to the battery, like 35 degrees C. And the lower temperature, 10 degrees C, is okay, but below 10 degrees C tend to damage the battery more quickly. So therefore, we test them at so our cooling system will maintain those battery temperature between 10 to 30 degrees C. So that's answer to the first part of the question. The second part is, why do we use MPC to optimize any system? The reason is this, because MPC is a model predictive control. We use the historical data of the building, like a different day and different time. Like a Monday to Friday, they're different. Saturday, Sunday are different. Morning and afternoon are different, right? So this is part of the information we have historically. Secondly, is the weather forecast information. And the third one is the solar generation history over the history. So we have this 3 information available. Therefore, we can predict the building usage, predict the generation, and predict how much battery energy we need to store ahead of time so that we can release them when it is needed. So that's why the MPC is very effective in this type of applications. Yeah, so that's that question. Let me see. I think there's another one. What are the governing equations or models that are used for the MPC? How accurate they are in predicting the load demands? Yes, good question. Well, the governing equation, basically, as I said, is the historical data from the building usage, the solar generation history, and the weather condition. They're quite accurate. Of course, we still correct them during the actual control. Now, for example, the demand charge is based on 15 minutes interval. So what we do is that for every minute, we measure the usage, and we compare to our prediction. If it's similar within the error band with our prediction, we keep them. If it's too much higher than our prediction, we actually reduce the usage in the second minute. So we maintain that 15 minutes average to be similar to what we have predicted. So that's what we're doing, right? Okay. So next.
So there is Since in chat box, you can check 2 questions which I have forwarded you.
Also, yeah, the chat box. What's the cost of making wireless charging machines? Well, the cost is related to the power level. You know, you can buy a cell phone wireless charger with low power, very cheap, $20, $30. But for EV charging system, also depending on power level, you can buy a 7 kilowatt charge, probably around $1,000. But the 22 kilowatts will probably going to cost you about $3,000. So that's all different. Very useful and interesting study. Thank you. I'm just curious to know what are the going. Okay, you already I answered that. Did you use CC and CV modes for charging? What do you think about the post charging towards the life cycle improvement? Yes, very good question. We do use CC and CV. However, we want to maintain the battery SOC between 10 to 90%. That we found very good for the battery life. So we rarely reach the constant voltage charging region in the second life. But during the laboratory testing, yes, we do the CV and CC charging. Post-charge is controversial. Some studies show that it can extend the battery life, but other studies showing that it's really not. So we have not really promoting the post-charging from our end. Okay, I think I have answered all the questions here.
Question: do you think about pulse charging towards? I think you have answered.
I answered that one.
Yes, I think you have answered.
Okay.
I think, sir, is there any alternative for lithium batteries?
Yes, very good question. Yes, and no. In fact, research in battery space is very extensive in the past like 20, 30 years. So lithium battery, if you think about it, is a new kind of battery. It was only available since 1992. And initially, people didn't believe lithium battery would work because it was the lithium ion was very unstable. But over time, they made it work. Not only they made it work, they improved the life cycle from a few times in the laboratory to now 3, 4, 5, 6,000 cycles. So the other research that is very heavily involved is solid-state battery. Solid-state battery research started, I would say, probably about 10 years ago, and by now, its progress is very impressive. People can already achieve roughly like 200 cycles. Now, 200 is not a lot, right? That's true, but they're making progress. Now, what's good about solid-state battery? Well, first of all, solid-state battery has much higher power density, energy density. So therefore, we don't need that much weight anymore, right? That's number one. Number two, solid-state battery is a lot cheaper than lithium-ion battery. They still use lithium-ion, but the electrolyte is solid, so it's relatively cheaper. So we can install more batteries. And lastly, they much safer. You can do nail penetration. They don't form short circuits inside internal short circuits, right? So they can operate at much higher temperature range. I mentioned about 10 to 30 with lithium-ion battery, but for solid-state batteries, they can operate up to minus 10 degrees C to 70 degrees C. So we don't need an active cooling. So that's another reduction in operating cost, right? So solid-state battery is also, I personally believe it's going to be something happening in the next 3 to 5 years. And once we have that, our EVs, it's going to become more popular because it's going to cost less money, last longer, and cheaper and lighter. So more efficiency, right? More energy savings. Yes.
That's interesting. Thank you so much, sir. I think that's all the questions which, and we are running on right time, like our technical session is about to start right now. Thank you so much, sir. And on behalf of IEEE IAS 2022 organizing committee, I would pay the gratitude for your valuable time and which you have spent. You have enlightened all the others and including me with your wonderful presentation. Thank you so much, sir, for your valuable time.
Thank you very much. I'll see you next year.
Sure, sir.
In person.
Yeah.
Okay, bye-bye.
Bye-bye, sir. Authors, please, I would request you to join the technical session. The link has been already shared. I hope you can join the corresponding or respective sessions which you want to give the presentation. Thank you so much. We are having in one more keynote in the evening from 4 to 5. I would expect all to join for the same. Thank you.